So students, in our previous video, we discussed the concurrency model of Verilog and how a module is structured. We looked at ports at the difference between wire and rich, and we saw how hardware executes all statements concurrently rather than line by line. Today, we are going to build on that foundation and go much deep into two very fundamental topics, data types and operators. Now, why are these two topics grouped together in the syllabus? Think about it this way. Every language, whether it is a spoken language, a programming language, or a hardware description language, is built out of two basic categories of built-in blocks, things and actions performed on those things. In grammar, we call these nouns and verbs. In Verilog, the data types, wire, reg, vectors, parameters, these are your nouns. They represent the signals and values in your design. The operators, the arithmetic operator, the logical operator, the bitwise operator, and so on. These are your verbs. They tell the hardware what to do with those signals. By the end of today's lecture, you should be comfortable reading almost any line of Verilog RTL code you encounter because between data types and operators, you will have covered the complete vocabulary used to describe combinational logic. As I mentioned in episode 3, that is our previous session, we introduced wire and rich briefly, just enough for you to understand program structure. I deliberately did not go into full depth at that time because I want you to first understand why these types exist before memorizing how to use them. Today we are going to cover every data type properly and then move into operators, which we have not touched at all yet. I want you to remember this line because I will be referring back to it throughout today's lecture. Data types are the nouns and operators are the verbs. Please write that down in your notebook. It is a simple sentence, but it will help you organize everything else you learn today into the correct mental category. Now, let us look at wire first. A wire represents a physical connection, nothing more, nothing less. Think of it exactly as you would think of a copper trace on a printed circuit board PCB or a jumper wire on your breadboard from the earlier practical session. A wire has no memory, it cannot remember or hold a value on its own. Whatever value is being driven onto it right now, that is its value. The moment the driving signal changes, the wire's value changes immediately. This leads to an important rule. A wire must be continuously driven by something, typically an assigned statement or the output of a gate. If nothing is driving a wire, its value is undefined. In simulation, you will see this is represented as a high impedance state written as Z. Look at the code example on the screen. Wire out, assign out equals to A and B. Here out is declared as a wire and it is continuously driven by the expression A and B. Anytime A or B changes, out updates immediately, automatically. You do not need to tell it to update. That is the nature of a continuous assignment, which we studied as data flow modeling back in previous lecture. Now, wire is also important because it is the default type in Verilog. If you declare a signal and do not explicitly say reg or wire, the compiler assumes wire. Keep that in mind. It is a common source of confusion for beginners. Now let's look at the right hand side rich. A rich short for register is fundamentally different in behavior. A reg holds its value between updates. It does not need continuous driving. Once assigned a value, it retains that value until it is explicitly assigned again. But, and this is critically important, so please pay close attention. A reg can only be assigned a value inside a procedural block. That means inside an always block or an initial block, you cannot write a sign to a reg. That combination is simply illegal syntax in Verilog. Look at the code example. Reg out always at the rate a comma b. Out equals to a and b. Notice the always at the rate a comma b. This is a procedural block that is sensitive to changes in A and B. Inside it, out is assigned using the equal to operator. And because we are inside an always block, out must be declared as rich. Now here is a point that trips up almost every student in this course at some stage. So listen carefully. The keyword reg does not necessarily mean that synthesis will produce an actual hardware flip-flop or register. The name is frankly a little misleading. Whether you reg becomes a real memory element or just plain combinational logic depends entirely on how you write the always block, specifically whether all in possible input combinations are accounted for. We will study this properly when we get into sequential circuit design in later unit. For now, just remember reg is a syntax category. It tells the compiler this signal is assigned procedurally. It is not by itself a hardware promise. Are there any question on wire versus reg before we proceed? Then do give comment. Now, so far every example we have used involves single bit signals, one wire, one bit. But real design almost never work with single bits. We work with buses, 8-bit buses, 32-bit addresses, and so on. This is where vector comes in. A vector is simply a wire or reg that has been declared with a bit range, allowing it to represent multiple bits on a single named signal. Look at the syntax. Wire 7 is to 0, data reg 3 is to count. The notation 7 is to 0 tells the compiler that data is 8-bit. You can say that data is 8-bit byte bus, with bit 7 being the MSB most significant bit and the bit 0 being the least significant bit LSB. Similarly, count is a 4-bit rich register. You can access individual bits or ranges using square bracket indexing. You can see here we are using square bracket. Data 7. This gives you just the MSB bit. Here you can see this is only the MSB bit 7. Data 3 is to 0. That is, this gives you the lower nibble bit 3 through 0. This is called the bit slicing and you will use it constantly. For example, when you need to separate an opcode field from a data field within a single instruction word. Now let's discuss parameters. Parameters. A parameter is a name constant. Why do we need this? Consider a design where you have hard-coded the number 8 in 15 different places throughout your code because your bus bit is 8 bit. So parameter bit is 8. Now suppose your design requirement changes, you need a 16-bit bus instead. You would have to hunt through your entire file and change that numbering every single location, which is error prone and frankly poor engineering practice. Instead, we declare a parameter with 8 wire with 1 is to 0 data. Now, if the bit need to change, you modify one line the parameter declaration and every dependent declaration in your module updates automatically. This also makes your code significantly more readable because with 1 is 1 colon 0 communicates intent far better than a bare unexplained number. This is good design discipline and I expect to see you using your parameters in your lab assignment going forward rather than hard coded numeric literals. Next is the operator landscape. Before we go category by category, I want you to see the complete picture first so that as we go deeper, you always know where we are in overall map. Verilog operator fall into 8 categories. They are listed on the screen: arithmetic, relational, logical, bitwise, shift, concatenation, conditional, reduction. I want you to copy this table into your notes exactly as shown because we will refer back to it repeatedly, not just today, but throughout the rest of this course. Every time you write an RTL expression, you are using operator from one or more of these 8 categories. Now let's go in detail of each category properly with worked example, starting with the two most intuitive ones, arithmetic and relational. Arithmetic and relational. On your left, we have arithmetic operations, that is addition, subtraction, multiplication, division, and modulus. These behave largely as you would expect from any programming language you have studied before. You can see that plus, minus, asterisk, then division, and then percentage, that is modulus. Now on the right, we have the relational operator, that is less than or equal to, greater than or equal to, and not equal to. I want you to note something important about relational operator. They always produce a one-bit result, either 1 representing true or 0 representing false. This makes them extremely useful for feeding directly into conditional statements or into the select line of a multiplexer, which, as you will recall from previous episode, we can express compactly using the conditional operator, which we will study shortly. Also, please be careful to distinguish between equal to and this equal to. A single equals sign is an assignment. It set a value. A double equal sign is a comparison. It checks equality and return true or false. This is a very common source of syntax and logic. Errors for beginners. So I want you to be deliberate every time you type an equal sign in your code. Now let's move to the next operator. The single most common point of confusion in this entire topic, logical versus bitwise. Logical versus bitwise, not the same thing. I want everyone's full attention for this slide. In every batch I have taught, this is the concept student confuse most often in their first lab exam. So let us go through it very carefully. On the left we have logical operator. Notice that double and looks almost identical to single and. The only difference is that one symbol is doubled and the other is single. But their behavior is completely different and this difference matters enormously in hardware design. And We have other logical operators too. On the right hand side, we are having bitwise operator and or tilt, and logical operator treat their entire operand as a single true or false value. Any non-zero value is treated as true. The result of a logical operation is always exactly one bit, one or zero, regardless of how wide the input operands are. Bitwise operators, on the other hand, operate independently on each bit positions in parallel across the full bit of operands. The result has the same bit width as the input. Let's work together the example on the screen together. That is A equals to 4 tick B0110. B equals to 4 tick B0001. Now if I compute A and B, this is a logical AND. Verilog looks at as a whole. Is it non-zero? Yes. Is B non-zero? Yes. Both are true, so the logical AND result is 1. Single bit. Now compare that to A and B. Same. A equals to 4 tick B0110. B equals to 4 tick B001. Now compare this. A and B. This is a bitwise and Verilog compares bit by bit. Bit 3 of A is 0, bit 3 of B is 0. You can see 0, 0. Here 1, 0. Here 1, 0. Here 0, 1. So as bit by bit comparison is go on, the final result is 4 tick, that is A and B is 4 tick B0000. That is bit by bit comparison gives the answer 0. A full 4-bit value is not a single bit. Did you see the difference? A, A and B gives 1 and A and B gives you 4 times 0. Same input, completely different operators, completely different results, both in value and in bit. This is not a minor detail. Using the wrong operator here will either cause a compilation with mismatch warning or worse, silently produce incorrect logic that only show up as a bug during simulation. I want you to develop the habit of pausing every single time you type an ampersand or a pipe symbol and asking yourself, do I want a single bit true false answer or do I want a bit by bit result? That question will tell you whether you need the logical or bitwise version. Are there any question? If then comment that question. We now cover 3 more operators categories that you will use extremely frequently in your RTL code. First, the shift operators. Left shift, right shift. These slide the bits of a value left or right by a specific number of position, filling the vacated position with zeros. There is a useful mathematical shortcut here, shifting left by n position. That is 2 to the power n. Mm. N position is equivalent to multiplying by 2 raised to power n. This is often used in hardware as a chip alternative to actual multiplication when the multiplier is a known power of 2. Second, the concatenation operators. This operator joins the multiple signals together end to end to form one wider signal. Look at the example, that is A, B and 2 tick B00, comma A square bracket 5 follows 0, which extends 6-bit value into an 8-bit value by prepending to 0 bit. Third, conditional operators. The ternary question mark. Look at the example out equals to cell question mark A colon B. This reads as if cell is true, out gets the value of A. Otherwise, out gets the value of B. I want you to recognize this immediately because this is exactly the multiplexer, because this is exactly the multiplexer example we built using data flow modeling. The conditional operator is in fact Verilog's built-in syntax for a two-input multiplexer expressed in a single line. The next category is often confuse students initially because the symbols are identical to the bitwise operator we discussed earlier, that are this uh, ampersand or and power operation. But here they are used as urinary operator, meaning they operate on only one operand, not two. A reduction operator takes a single multi-bit signal and collapses it down into a single output bit by applying the operator successfully across every bit on that signal. Let's work through the example. A equals to 40, B 1101. If I write ampersand A, this is the AND reduction of A. Verilog effectively computes bit 0 and bit 1 and bit 2 and bit 3 all the way across. Since not every bit of A is 1, so we are getting 0 as a result. You can see. If I write pipeline A, not this is the OR reduction. Verilog computes bit 0 or bit 1 or bit 2 or bit 3. Since at least one bit is 1, at least one bit is 1, so you are getting 1 as the result. Why is this useful in practice? Reduction operator let you answer question like, are all bits of this bus equal to 1, or is at least one bit of this bus set, without writing a large unwieldy conditional expression co- covering every bit individually. You will see this pattern every often when implementing status flags such as all ones, a detected flag, or a parity style check using the XOR reduction operator. I want you to be very deliberate about the distinction between single ampersand used between two operands, which is bitwise, and used before a single operand, which is reduction. The context, specifically the number of operands, is what tells you which one you are looking at. Now, let us look at this code as a complete unit. This is a small arithmetic logic unit style fragment, and I want you to identify line by line which operator category is being used before I tell you. Parameter W equals to 8, wire W is 1 colon 10 AB sum band shifted wire EQ all ones assign sum A plus B, assign B and assign shifted, assign equals, assign all ones, assign results. So there in this we are using all the operators we have studied. Let's walk through this together. The parameter W sets our bus width to 8, which that's our name constant from earlier. We declare our vector signal. Then sum uses the arithmetic operator plus operator. Band uses the bitwise AND operator. Notice it's between two operands. So it is a bitwise, not reduction. Shifted uses the shift operator. EQ uses the relational operator. Wrapped from clarity. All underscore ones uses the reduction and operator. Here it is a single operand A. So this is the urinary reduction form, not bitwise. And finally results uses the conditional ternary operator. You can see there is a colon selecting between sum and band, depending on whether EQ is true. I want you to notice something in 6 lines of code. We have used 6 different operator categories, and this is not a contrived example. This is generally representative of a kind of RTL. You will be writing for the rest of this course and indeed in real industry project. If you are comfortable with everything on this slide, then you are comfortable with the majority of combinational Verilog syntax you will encounter. Before we close today's session, I want to leave you with one consolidated rule, something you can recall instantly during your lab exam, even under time pressure. Single symbol means bitwise. You have to remember this single symbol bitwise. Double symbol logical. Single and single or single symbols operate bit by bit and produce a full fifth result. Double and double or. Double symbols treat the entire operand as a one true or false value and always produce a single bit result. Please write this down, box it, underline it, whatever memory technique works for you. I promise you this exact distinction will appear in some form in your next semester exam, and most importantly it will save your real debugging time in your lab work, because a bitwise versus logical mistake is one of those bugs that compiles cleanly and only reveals itself as incorrect simulation output. And that brings us to an end of today's topic. Let's quickly summarize. We covered wire and reg in full depth. We covered vector and parameter for representing multi-bit and constant values. And we covered all 8 categories of Verilog operator with worked examples for each. With this, you now have the complete vocabulary, the nouns and the verbs needed to read and write combinational RTL code. In our next session, we move from vocabulary into actual verification. We will study the parts of simulation, specifically the design block and the stimulus block, and you will write your very first test bench in the lab. I would encourage you to review today's operator table once more before that session, since your test bench will make use of relational and logical operator when checking expected outputs against actual outputs. Are there any final questions before we close up this lecture? Then comment in the comment box. I will see you in the next lecture. If you enjoy this operators and data type journey, then share this with your friends and subscribe the channel. Thanks for watching.